Hello, welcome to Dev Radio, and I'm here with Diego Casati, who is one of our global black belts, which means that he is a technical expert who we kind of drop down into our big customers to solve hard problems with them. Did I describe what a GBB does, Diego?
I think you did. Yeah. Appreciate you, and also the chance of being here and sharing some of this.
Yeah, I think what you've got to talk about is pretty cool. So the project is Project Stormbreaker. And it is about predicting the impact of storms, which is a pretty challenging predictive analytics problem, and takes a lot of, well, traditionally it takes a lot of heavy iron, a lot of compute. But actually, why don't you just go ahead and you take it from here? You're the expert. Why don't you tell me about who asked us to do this and why, and what problem are we solving?
Yeah, I think you did a great job there. I mean, to be honest, this is a tough job, and traditionally we're going to be using supercomputers. We still are using supercomputers. So when you look at NOAA and the big government bodies in the globe that are trying to simulate this, you need supercomputers because you need CPU power to be able to forecast and understand things like hurricanes and the massive amount of water they can move and all that. The ask here actually came from a customer. And the challenge, if you will, was, can we do something similar? We don't have a supercomputer, or maybe we do. Maybe Azure is the actual supercomputer here. Let's go with the idea that there's a chance here that we're going to be using Kubernetes. So in this case, AKS, Azure Kubernetes Service, to do what traditionally an HPC platform or solution would do. So that's the premise here. Can that even be done? Right? That was the question back in January of 2024. What we end up having today is a platform. Kubernetes per se, we typically say that Kubernetes is a platform that you can build platforms on top. And I think this is a great example of that, to be honest.
Yeah.
And the core point here would be, can we make it so other folks that don't have an actual supercomputer like NOAA could use what we have, right, in Azure?
Yeah. So I think do you want to take us through? I mean, they were doing this before, and they kind of had like some benchmark numbers that they were going after, right? That they wanted to see if we could do it just like them. What were kind of the constraints we had to work with to make this work right?
Yeah, so there's a ton of, and I'll go into just a little bit of the architecture in there in a second here. Maybe I'll leave it in there, but there are a ton of challenges in here. One of which is we are dealing with layers of abstraction to get this to work. Traditionally, in an HPC, in a high-performance computing environment, you're going bare metal at this point.
Yeah.
Are you using the highest CPU with the highest clock, or with the most amount of buffers and things like that? You're doing things like NUMA to locate and co-locate memory and core. You're also looking into networking. So we're thinking of InfiniBand and having, let's say, 40 gigabits per second. That's not your traditional Kubernetes workload. It was probably not even designed with that in mind. It was designed to take care of some other problems. But it turns out, and again, we did have benchmarks, and those benchmarks were already quite aggressive. It turns out you can do. As a side note here, I feel like it's interesting the times you were living in, that AI and the fact that a lot of the AI workloads will use InfiniBand. There's a lot of progress on making that stack that runs AI something that we can also run, like what we're seeing here, which is essentially a CPU-based workload. So we're benefiting, if you will, left and right from that work that has been enhanced and developed with AI that you can now see in a traditional HPC workload running on Kubernetes.
Yeah.
One of the things that, since you mentioned just about the performance there, and I I'm happy to go a little bit more in detail into this, is that there are decisions here that needed to be made so that I can get the utmost performance. So I'm looking into not only, again, the size, what's the SKU in Azure for the VM that we're going to be using, which in this case, we're using the HB series from AMD, and that's the family version 3. We actually have a version 4 now available. Version 3, specifically here using the EPYC family of processors, we can get a substantial amount of performance. Originally, the workload that I'm running against was also running against EPYC, so you're kind of starting at the same place there. But from just an architecture point of view, and as you were trying to make the solution a little more viable and again faster, what else can we do that traditionally you would be doing with an HPC stack here, and then moving, the concept of just an HPC play into more of an app innovation end-to-end solution with Kubernetes being that I call this like the Lego building block plus because you can do so much more, right, with what we have there.
Yeah, so I mean, really, at the end of the day, this was something that it's a pattern that we'll be able to extend to other things, other scenarios that require, this level of computing intensity. So,
Absolutely.
yeah.
I think
Yeah.
the lessons learned, I mean, this started with, we're doing weather modeling and simulations, but I feel like as time went by, we all realized that there is an emerging pattern here,
Yeah.
that when put it together, we can run other workloads. So yes, I think weather simulation is probably one of the things we think about, but there are many different HPC workloads out there. That's just one of them, right? And I think it's the one that actually speaks to everybody at this point in time, because we're thinking about tsunamis and hurricanes and tornadoes and things like that. But we can, whatever, pretty much, I want to say that you can execute on a traditional HPC platform, chances are we can do it in here.
Yeah. But this, I mean, I know that this project had a few interesting challenges of its own. I remember talking about, containerizing Fortran.
Yes.
Do you want to tell us a little bit about how you when it came time to actually build it, what did you have to figure out?
So yes, there's I don't think so. I'm gonna paraphrase that, saying that that wasn't my in my to-do list. I did not imagine that I had in your bucket list as a professional, like I'm gonna work Fortran in 2024. None of that was a part of this. However, it turns out, and it's surprisingly how it's a mix of really cutting edge new technology, if you will. It's part of the stack here. So I'm looking at AKS with the latest and greatest hardware and all that with the HB series. But at the same time, these models are done in Fortran, and they've been proven to be working for a long time. So I'm using what is called advanced circulation. It's one of the solvers, essentially, our model here, that it's coming from academia, and it is done in Fortran. And there are few people out there that can still write this up to this day. There's a high level of confidence from the scientific community on these models. Now, how do you actually get that to be linked against some C++ programs and also some of the Fortran interpreters, if you will, out there? So I went into a path here of, well, okay, let me see how this compiles, and there's a lot of lessons learned about that, and having this done in Docker. And so the way you approach this, is slightly different than a traditional way of just putting something in a Docker and call it a day, because that application AdCirc, the advanced circulation application, when it compiles, it is actually looking specifically at a hardware level. So I had to spin up one of these VMs, one of the HB series, and then run and develop against that. So I had VS Code. I'm doing a remote host connection, so essentially an SSH tunnel, and then doing it step by step, trying to understand. So this went into the challenge here was, what flags do I need to pass to CMake for this to happen? So it's G4Tran, GCC, CMake. I think I joked with you originally, like this brought me back to my BSD days or Slack, where when you're doing everything, there's a ton of make files. So at that point, you're passing specific flags so that when GCC compiles this binary, the optimization is going to optimization level 3 or specific architectures. I have the files here on GitHub. We'll share the link with everybody. So if you're curious about this, you will be able to, under our default directory, there is a Docker build. And in the Docker build, you can see that. So it is kind of interesting. And I tried my best here to also, you can see like G4Tran, M4, the GNU Auto tools, they're all in there. All of the libraries and how you link things. This kind of, again, this is a mix of going back to a traditional way from a Unix perspective, really, or Unix-like perspective here. This is how my career started, which is interesting too, because when we think about a sysadmin and how that role developed into what we have today, traditional Unix or Linux or BSD sysadmins, they were doing what I'm showing you here, right? They were compiling things and maybe patching things as well. I did some patching across the way here to get things done. And it is a slightly different mentality that kind of went away, I feel like, maybe in the 2000s or so. And then it's back now when you talk about SRE teams and all that. So there is an interesting journey in here, if that makes sense there. But yeah, to your point, it's all in here. The flags are in there. So a ton of interesting lessons learned. Now, if we go back here just a little, just to recap, we get this massive computers now that we can use with Fortran. Now I have a second challenge, which is how do I actually use and orchestrate that? Because if you go and just look at Kubernetes, it wasn't designed to run HPC workloads. So you don't want to use, it's a job, but you don't want to use the default job facilities that Kubernetes presents you at that point. So the approach here, there are a few approaches. The approach that I end up going with is to use an HPC scheduler that was designed from a cloud native perspective. It's actually part of the CNCF at this point, the Cloud Native Foundation, as a project, and that's called Volcano. So let's take a step back. We have AKS, we have this workload in Fortran, and then now we're gonna schedule that with a scheduler that was designed to run on top of Kubernetes, and that's Volcano. What Volcano allows you is to follow some of the guidelines or some of the frameworks that were already available from an HPC perspective, including, we're going to now look at how many VMs we have. So in the diagram here, I have 3 different VMs. And, if I were to use all of the 120 CPUs in each one of those VMs or in those nodes in Kubernetes terms, I can now have a queue up to 360 cores. And that's something that when you're designing for HPC, you're thinking about. Like, this is the size of my queue. So whenever I'm scheduling tasks or jobs, I can carve out a chunk out of that queue. Unfortunately, here I can't really do that because I need to give some of those cores to Kubernetes itself, to Linux kernel, and whatnot. But it's still highly doable. So I'm using a concept of a queue with Volcano. And then after that, we're running a main or a master job that will run the parts of the solver, or like AdCirc, which is the workload, in the different nodes or in the different virtual machines. Everything here at this point becomes very traditional HPC. We have something called MPI as an interface here to pass messages in HPC and to share the workload across the different nodes. I'm doing Open MPI for that. And we're talking with these nodes using SSH. Again, there are other ways to do it, but SSH is how I get it done. At the end of the day, you would be able to get pretty much any workload that you can run with MPI using the pattern that I have here. And this is something that it started the way I'm telling you, which is the middle part of our diagram. And then it expanded out to all of the perimeter there. And again, being a container platform like AKS here allows me a lot of leeway. I can try things out, and if they don't work, I just remove the container. There's nothing to be installed anywhere, which is really, I feel like that is an aspect of this that we talk to customers all the time as GBBs, where even if you're not taking potentially Kubernetes to its full extent, and I am in this case, the fact that you can containerize, have it schedule it, you can instrument your code, because there's also that.
Yeah.
All of that will give you, from a business perspective, a lot of value, because you can really reiterate really fast on this cycle. But from a SRE team or developer perspective, it's almost like a dream coming true at this point, because I can have, and I have, about 5 versions of the same container where I'm experimenting with different flags. And then I have on the monitoring stack Prometheus and Grafana, and I'm looking, okay, if I enable these flags at the end of the day, does it change anything? I can check that, because the whole stack is now fully instrumented. I can look at the network level, I can look at the storage layer, at the CPU, and get those metrics.
Yeah. How long did you work on this project? You did it pretty fast.
So about 3 months, I want to say.
Yeah.
Again, this speaks a lot to me, and I feel like this would be something that I would be happy to bring back to the community. So yeah, about 3 months on this.
Wow.
One of the things that I want to say here is, you take something like Fortran, which is, for all intents and purposes here, I mean, it's a niche language here, or frame. I don't even know that I want to say if it's a framework. It's niche. You don't find people that actually know Fortran. It's very rare, right? I mean, at least I didn't know anybody until this. How do you go about that? Which is interesting. I mean, to me, I had to talk to actual scientists that are doing weather simulation and knew Fortran. Again, probably very niche. But at the same time, we as a company, and I think just as an industry, we're coming out with all sorts of Copilot and GPTs. So I'm also using GPT-4 to help me out.
Yeah. Just
as essentially a coding buddy here, somebody that I could talk to and ask some questions. And the moment I got a stack trace, it was scary. It was like, I don't even understand what's happening here.
Yeah.
So there's that.
That's where the code developer Copilot really comes in handy.
100%.
Yeah.
100%. So you asked me how long it took me. Like, I don't, so the 3 months here, it would probably be a 2-fold or maybe 3-fold in time.
Yeah.
If I didn't have any assistant, and assistants did come through GPT and AI and Copilot and all that. Like I use it all when I could, because I need to understand what's going on.
Yeah.
One other thing that I feel like it's of interest here is that as I moved along, and and I'm trying all of these different scenarios with AKS, the AKS team didn't stop releasing things. So as they were releasing new things, so AKS Automatic is just the latest one, I'm now looking to incorporate that into what you see here. Yeah. Because again, at the end of the day, the audience here, the target audience, are folks that are either doing HPC, and I want to alleviate the decisions behind the scenes here. I don't think, I mean, if we can give some opinion based on industry standards or things that we are seeing, or the product group is experiencing seeing, I think that's a plus. So as I'm developing this, and I'm also talking to some folks in engineering, that is interested on their side to understand it, but I'm also looking back at them and say, okay, what else can I do here that will make a scientist or an operator life easier?
Yeah.
Manager Prometheus, Manager Grafana, they were already in there.
Yeah.
Almost a no-brainer at that point. I said, I'm going to enable this, and we're going to instrument as much as I could a code that nobody really understands, like, or a few people understand, which is Fortran. But when I went back to the AKS team, I also am looking at what else are you releasing here so that I can incorporate. And automatic is likely the next round of this whole thing. Here would be, let's make it so it abides to automatic, or just use automatic, and we'll go from there. So I think again, you can see that the pattern here is something that can grow over time. I mean, I saw firsthand, like, it is changing and growing over time, just with the new things that these guys are coming out, which is a lot of really interesting things that make the AKS team is putting out.
Yeah. So this is normally a process that takes quite a while to run, but can we do any kind of demo?
Yes, we can.
Yeah.
So we'll do it live. How about that?
Okay. Those are the best.
We'll do it live. I will just go over real quick what we have here, and then we'll go into the Stormbreaker terminal, and I'll show you live. So a couple of things that we have here from an AKS perspective. We do have a system node pool, and that system node pool is where I have Volcano, so it would be on this side here. I'm using Kada. That's the Kubernetes event-driven autoscaler. Traditionally, Kubernetes will scale its running containers or pods in Kubernetes language here using CPU or memory. So if you give rules saying my application here, the moment is above, let's say 75% CPU, I want another copy, right? So you're basing that decision on a CPU. You can also do that based on memory. The way to extend that is through Kada. Kada is likely the number one option for that. So with Kada, I'm now looking at a couple of things. One, I have a service bus queue where I have the jobs that are created by the user. So when a user or an operator comes in, and we're going to be doing that ourselves, we create a new job, a new simulation, put that in a queue, and then Kada essentially wakes up because it's monitoring that service bus queue, and it moves the job around between a dispatch queue, a running queue, and a completed queue. So it is interesting here too that before, I want to say maybe last year, you'd have to install Kada out of band. And right now, this is just an add-on. Again, I'm tapping on the fact that AKS on its own, right, and the work being done there is progressively getting better and better and better. So the fact that the team now enables you to just have a flag and you have Kada, that's a fantastic thing from a developer perspective. Hey, I have now a way to do event-driven architecture, and then tap that with Kubernetes or AKS here, right? And I do use it. So we have Kada running. I also have another Kada component here that wakes up and looks at a storage account, and we are using that over here with the Azure Data Lake Gen 2, the second generation, where I have essentially two containers in blob storage. One is my input, where I'm reading the template. So the template files from what simulations do I want to run? And right now I have 3 of them. I mean, the sky is the limit at this point. So I read that out. And then once the job is processed, we're going to save that out into the output. ADLS second generation here allows you to mount its containers here in blob storage through NFS version 3, which is also important because, again, that allows me to have all of the jobs running and then writing back or reading directly from blob storage. So I'm decoupling the whole state from the cluster. Everything is kept outside. In the cluster itself, you won't see this directly there, but you will see when I show you the terminal. Steve Griffith and myself from my team. Steve's also from my team. He is HBB located in New York. And he and I designed a solution around an NFS server that runs local in the cluster. which is kind of interesting too. So you ask an issue like about the challenges here. One challenge is that you don't want to move data in and out to blob storage. You want to try to keep it in the clusters as much as you can because you're doing a lot of work around that with the different jobs or tasks running. That NFS server takes one thing into consideration here. These big VMs, they have 2 NVMEs physically on them. So what we do is we carve out one of them, we mount them, we create a file system, and then we expose that through an export to the rest of the cluster. So all of that information is now kept in the cluster. We iterate over it, and then at the end, and I'll show you that in the code here in a bit, we save and package the whole output, and then we ship that over into Blob through NFS. So that would go into your output. All of these decisions here, when accounted for, essentially will give you the performance that we're able to get, right? So the local NFS server is one of them for sure. And the fact that we're using NVMEs. I did try other options, UltraDisk, SSDs, and even RAM, using a RAM disk. RAM and NVMe have very similar IOPS and bandwidth, so I just went with NVMe, and this resulted in some pretty good performance benchmarking. All that said, I think you're eager to see the demo, and I will show you the demo now. So in here, what we have, we are calling this a Stormbreaker terminal. The first iteration of this was very 1980s, and I think it showed my age right away. So I asked Cindy Wang from my team. She's also part of the App Innovation Global Black Belt team for the Americas. And she came up with a great design here. One of the features that I joked to you about is a dark mode here. I love the dark mode. It's a selling feature. Yeah. The terminal right now runs in the cluster. So I'm tunneling to the cluster. There's nothing exposed to the internet here. You can see localhost. And this will allow us to create a job. And we'll do that in a second here. So we'll have a dashboard with the running jobs. Right now, there's nothing running there. We can create a new job. And then we just have a little bit of an about information in case folks want to see more. That will point back to our GitHub repo. In this very simplified dashboard, we have ways to create and delete jobs. You're not really changing an MPI job once that's running. You're either deleting or you're creating. So to create one, we have a few parameters in here. So let's suppose we wanted to get the city of Miami here. I can see I already have done this before. So let's go over the parameters. I'm going to, in a hypothetical scenario here, I'm doing this for the city of Miami. And then I can choose one of the simulations. They're very different. I'm going to do Katrina here just because of the time we have. If I were to run, let's say, the model for Guam, that's likely taking about 2.5 hours for that to happen. If you're doing Gustav, which is a huge hurricane, that might take more time as well. Now, the time here changes depending on the hardware. So for Katrina, I'm going to be using the smallest version that I can out of the HB120 family, which is the one with 16 cores and version 3. But you can see I left some options here. For a large simulation, so I'm thinking like Guam, I'm going with 120 at its full capacity at that level. But just for now, we're going to go for the 16. Then, again, that's something that user could change here. I'm going to let 3 nodes to run. I'm going to go down into 36 cores, and this will become clear in a second, and then 12. Now, why am I doing that? Well, each one of these VMs, they actually have 16 cores. I want to reserve in each one of them a little bit, so 4 cores in each one of them, just for Kubernetes, Linux kernel, and all of that. The moment I give the system 12 cores, it will absolutely take those 12 cores, and it will run at 100% of CPU for the duration of the job here. So you're not counting on those anymore. So 3 nodes, so 3 virtual machines times 12 gives me 36. And we save it. That's now getting dispatched. Behind the scenes, I'm going to move this now into our view. This is how it looks like. We have service bus with a new job, and you can see Kata just woke up, which is this dispatcher. And after that, you can see that I have a job under called with this UUID, that's the master, and then the worker nodes. As we're pulling these images into the cluster, this just might take a second here. You can see they're running. And then the master node is now ready to go. Once that's happening, this is an actual output of Katrina. That's the simulation that scientists will be looking into. You have the speed of the wind and things of that nature, elevation and water and whatnot. Once that job is done, which you just did there, again, the MPI master here will wrap that up. It will send it. It's all running on this NFS server down here. It will copy that into Blob. It will see that all the jobs will get grayed out. Just happened. And then Kata will come in and then clear all the queues for the user. So when this whole orchestra works, this is how it works. You would see all of these different components with event-driven architecture behind the scenes, just making sure that we move the right pieces to the right place. And then you can see the rest of the running containers or pods in the system here, just keeping the workflow. As this happened, if the user comes back to the dashboard, that's now gone. So we can take it from here now and then explore this in many other ways. But as it stands, we did our simulation, which if you do it in a single computer, that's going to take some time. I'm going to tell you that right now. You need to be very patient. If you go back to your terminal here real quick, I want to show you what we have. So we have 3 different nodes in here. These are the really large nodes. Right now they're just the 16 cores, but again, because of the family that I can scale this up and have the 120 cores available. And then I have the system node pool with redundancy here. We have 2 of them. When we have this HPC SKUs here, the HB series, we actually use the NVIDIA operator just to facilitate our lives and have all of the InfiniBand drivers installed and all that. Again, coming back to things that we're getting from just the development on AI. This is one of like the byproducts, if you will, of that, which is amazing because it allows us to do what we just did now, and get these weather simulations. And then maybe lastly on that is that we can have, again, I mentioned that I have this fully instrumented. So, well, I'll show you how that looks like. So we're going to connect into our Grafana dashboard. And from an operator perspective here, one thing that I want to highlight is that this is all of what I'm showing here, all these dashboards, they are highly configurable. We're using Managed Grafana in Azure, but I didn't do any of this. This is out of the box. I did not have to change any of that. I just enable a flag and then I'm off to the races, which is, again, pretty amazing for trying to get this up to speed. Yeah. I can now see all of this information from a performance perspective, and you can see when we just ran here, you can see the memory spiking up. You can see the jobs and how long they took to run in here, bandwidth, memory, rates of package. They also give you, I'm a fan of Brandon Gregg. I don't know if you're familiar with Brandon Gregg. He's famous for performance benchmarking. Is the guy, I think his come to the fame here was that he was screaming some JBods in a data center when he was doing some eBPF. He's amazing. And he, I think, brought us the use method. And it's something that as a performance engineer, I've used it before. So that stands for usage, saturation, and error. Again, we get this out of the box with what we're doing. And if we go and trying to understand these different models, and we're, again, talking about Fortran here at this point, it is interesting the fact that we can actually see that, and then we can do some inference here. Okay, is it CPU bound? Is it memory? Is it network? Well, right now I can tell you how that works because I'm looking at one of the nodes. And I'll tell you right now, it is CPU. It's CPU bound. So all in all, I think that if we go back here, this whole stack, the fact that we have that, the fact that we can schedule and have observability would allow as a pattern for other folks to come in and reuse this and then potentially run, you name it. I mean, maybe it is water based, maybe it's something related to space weather, or
Yeah.
there are so many use cases right now. Also to mention, the whole setup is done with infrastructure as code. I think I talked to you about that at a certain point. So you could change anything here. You keep this information in something like GitHub or ADO, and you go from there. I did most of my development on GitHub, and I did most of my development using a dev container, in fact.
Yeah. Oh, wow. And so really what, I mean, so at the end of the day, what we have is a platform that can trigger really complex workloads, but you can put that power into the hands of just a data scientist, for example, so that more people can more easily explore it. And scientists are awesome at showing us what is possible. But this kind of, takes it to not quite democratizing, but getting it in the hands of more people for sure.
Yeah, that's the core, I think. Yeah,
Yeah.
I think that the moment I'm going over here and then just creating a job and the reaction is, oh, is that it, or is that simple? I think I've achieved what I was trying to do. That's the mission.
Yeah.
Right? The mission isn't to show the complexity. As engineers, I feel like we sometimes love the complexity, understanding things. This is probably why we went to engineering school. That's certainly why I did.
Yeah.
However, the end result here, to your point, it is to make it easier for folks. I mean, I wanted to be an experience that is almost seamless, like you have your data. Because at the end of the day, you and I and our families and our friends, we rely on these alerts, right? We rely on folks making predictions. If I can make their life easier, man, I think that I've achieved my mission on this planet here.
Easier and more automatic.
Yes. If we can make it easier and more automatic, you've hit the two right spots, in my opinion.
Is there more that we want to cover before we go, or?
No, to be honest, I'm happy to have any contributions here. If folks, we're gonna share the link for that.
Yeah.
You can go with just using it and just having fun with it and potentially, hopefully, getting some value out of it.
Yeah.
Or if you want to go a little deeper and understand everything is open source, everything is on GitHub. I made sure also to document all of the sequence diagrams. And we have a C4 diagram that shows how things talk to each other. I do love my my diagram. It's a bit of an architecture. I love it. I try to put as much as information as possible. But I also have, if you are into, I need to understand how this works in a low level detail, it's all in there. I have sequence diagram for everything. And we have everything done in Plant UML through VS Code. So everything can be modified here. Nothing in here is proprietary. Nothing in here is, essentially locking you down in any shape or form. So reach out. I would love to hear from different use cases and how we could help others.
Yeah. Awesome. Well, thank you for sharing. This is so cool. I mean, I could not have imagined this being done a year ago. So.
Well, that was me in January.
Yeah.
But and there's a lot of incentive from a lot of folks, and it is what you see now. So happy to share this with more people.
Awesome. Thanks so much.
Well, thank you for having me.